Hello, today we are going to talk about all the different units, constants, conversions, prefixes, and stuff like that, all the basics that you're going to need to know for the MCAT. So we're going to go over the SI units and prefixes such as tetra, giga, mega, pico, what all of those mean, and then we're going to go over different constants that you're going to need to know, like the speed of light, Avogadro's number, stuff like that. We'll also talk about the variables that you'll use for these various things, and then while we're going through and memorizing all of these values and constants, we're going to go over the conversions, how to convert from one unit to the other unit, and some different tips and tricks that might help you with either the chemistry or the physics section, any ones of those, or just really anything that has to do with math and units. So let's get started. So first I want to talk about all the different prefixes that you're going to need to know for the SI units and conversions. So by prefixes, I mean like micro, milli, stuff like that, and what their associated 10 to the power of X would be. So we're going to start at the biggest and then work our way to the smallest. So for all of these, I'm going to write out what the term is called, the symbol that we're going to use for it, the multiplier to the power of 10, what we're going to use for it. First we have tetra, or T, and this is going to be 10 to the 12th power. So this is the biggest one that we are going to see. Next is giga, and you'll see this just as an uppercase G, and this is 10 to the 9. Going down we have mega, this is an M, and this is going to be 10 to the 6. Now we get to kilo, and this one is more commonly used than some of these other big ones. For chemistry, we tend to use the smaller ones more when we get down to like micro and pico and stuff, but for physics we use a lot of these kilos, as you might know, kilograms, stuff like that. Now going below 10, we're gonna get to centi, which is just a lowercase c. This is 10 to the negative 2 centimeters. Milli, lowercase m, 10 to the negative 3. All right, micro. This one is used a lot. This is used by the letter mu, is what that is called, and that is 10 to the negative 6. Now we get down to nano. This one is just a lowercase n, 10 to the negative 9. And then the very last one that we are going to discuss is pico. Pico is a lowercase p, and that is going to be 10 to the negative 12. All right, let's zoom out. So these are all of our prefixes that we're going to use, all the way from 10 to the power of 12 to 10 to the power of negative 12. So all of these negative ones are going to be very, very small numbers, and some of these might seem familiar to you. Centimeters, millimeters, stuff like that. A lot of the times micro, we'll see that in volume, microliters, if you've ever encountered that before. Some of these bigger ones, tetra, giga, we don't see as much, but definitely still worth being comfortable with those. Now let's move down to some different conversions. And so these conversions, if you understand these prefixes, you'll be able to do on your own without memorizing these, but sometimes just memorizing some of these ones that you'll use very frequently will be easier. All right, so let's start with length. So the SI unit for length is meters, and by SI unit, I mean the unit that we're gonna use in all of our equations. So let's say we're trying to find the spring constant or something, and we're going to use F equals negative kx. X is for length, and the units that we're going to use for that are going to be SI units. So we're always going to use meters. If it's given to you in something other than meters, you're going to need to use these conversions to change it into what the value would be in meters. So 1 meter is standard. Now, this is equal to 100 centimeters, where if we zoom out, we said centi was 10 to the negative 2, so that should make sense. We have 2 zeros on the centimeter, so we just move the decimal over twice and you get straight to meters. Now, 1 meter is also 1,000 millimeters. You will use this conversion a lot too. Milli, we said, was 10 to the negative 3, so we moved that decimal point over 3 times, which would get us to 1. And we'll do some dimensional analysis and conversions and math on this in a second. And then lastly, I'm going to say that 1 kilometer is 1,000 meters. This might seem pretty straightforward, but when you're doing conversions and you're moving the decimals over, it's very easy to get them confused and mixed up. Next, we're going to move on to mass. This is very similar to length as we just did. The SI unit for mass is going to be kilograms. So I know it's a little confusing. I said meters is the SI unit for length, but kilograms is going to be the SI unit for mass. So just remembering that. So 1 kilogram is the same as 1,000 grams. Again, 10 to the 3. We said kilo was 10 to the 3. We moved that decimal point over 3 times. We can also say 1 gram is 1,000 milligrams. Very similar to what we did up here with 1 meter is 1,000 millimeters. That prefix milli is the same. We just moved the decimal over 3 points. Sorry if I'm being redundant. This is just very good foundational knowledge to have. And once you have these down, building off of it and using all the equations and doing math off of this will be so much easier. Let's move on to volume. SI unit for volume is 1 liter. 1 liter is the same as 1,000 milliliters, again, milli. Another important thing to note is that 1 milliliter is the same as 1 centimeter cubed. So I'm going to highlight that one because that is not just units that we would usually see for volume. Knowing this conversion is very helpful. This is just something that you're just going to have to memorize. Going off of this same logic, we can also say that 1 meter cubed is the same as 1,000 liters. All right. Okay, now for time, we're going to go over an example of dimensional analysis, how you would change from one unit to another unit. So our goal, I'll write down, is say, we're gonna try to find how many seconds are in a day. All right, so let's start off with 1 day. So the goal is to get from 1 day to seconds. So we're trying to change the units from day to seconds, but we want the number, the magnitude of the value to be the same. We want it to equal the same thing. We just want the units to be different. So we're gonna start off what we have, and we're gonna think, okay, what is the next step down that we can go from day on our path to seconds? And so most likely what you're going to think of is hours. So next we're going to put hours on top and day on the bottom. And we're going to do this because when we put day on the bottom, they cancel out. If we have a fraction with one thing on the top and one thing on the bottom, it just cancels out to be 1. So that's why we're putting day on the bottom and we're putting hours on the top, because that's the goal. That's what we're trying to get to. So we need this value to equal 1. And why do we need it to equal 1 is because we don't want to change the value of the number at all. So we want to multiply 1 day by 1s over and over and over again until we get a different unit, but we want the value to stay the same. So how we would do this is we could say 24 hours is the same as 1 day. So that cancels out to be 1. 24 hours in 1 day is the same thing, just different units. So we just multiplied by 1, so the value is the same. Next, we'll think, okay, what's the next step down from hours? We're going to put hours on the bottom because we want to cancel out hours. That is not our goal. And the next one would be minutes. So we'll put minutes on top. We can say that 1 hour is the same as 60 minutes. Okay, that cancels out to 1. Those are the exact same things. They're just different units. Okay, so we canceled out days, we canceled out hours, now we have minutes. Now, the next step is our goal. We can go straight from minutes to seconds because we know that relationship. We can say, we'll put minutes down at the bottom because we want to cancel it out, and we'll put seconds on top because that is our goal. We'll cancel out these minutes and we'll say that 60 seconds is the same as 1 minute. Now that all of our units have canceled out, the only thing we have left is seconds. So we're going to go ahead and multiply all of this out. So we'll do the numerator, which is 1 times 24 times 60 times 60, which is 86,400. And then we have seconds. And we can go ahead and do the denominator. It's just equal to 1 because all of these cancel out. So we can thereby say that 1 day is equal to 86,400 seconds. Now, this is not a number that you're going to have to memorize. If you want to, you can, but this is just an example of how to use dimensional analysis, how to change from one unit to another unit. And basically the premise is just multiplying by 1 over and over again to change the units so that they cancel out. All right, that was time. Now we're going to move on to temperature. All right, the SI units for temperature is Kelvin, and Kelvin is Celsius plus 273. So if you're using, let's say, the ideal gas law and you want to use PV equals nRT, for temperature, you're going to use Kelvin unless they give you a different constant for R that has different units. You'll have to really pay attention to these units because most of the time you will use SI units in your equations, but sometimes they will give constants for you to use with different units than the SI units, and you're going to have to look at the units and be able to decipher what units you need to use in order to figure that out. For example, PV equals nRT. The gas constant R is usually given in units of joules per mole Kelvin, and that is standard SI units. But let's say, for example, they gave you the value of R and they said that the units was joules per moles Fahrenheit. Then you would have to realize, okay, we're not working in SI units. I need to match my units to what the gas constant is that they gave me. It's all about unit cancellations. Once you do more physics and more chemistry problems, this will become more like second nature. All right, and the conversion from Fahrenheit to Celsius is fairly confusing. I'm not sure how high yield this is, but just if you want to have it in your notes, Celsius is 5/9 times the Fahrenheit minus 32. A little confusing. Most of the time they'll give you the conversion if they're going to give you stuff in Fahrenheit, or they'll give you a constant that is also in terms of Fahrenheit. All right, moving on to pressure. Most of the time for pressure we are working in atmosphere, so ATM. But it is important to note that they could also give it in terms of millimeters. 1 ATM is the same as 760 millimeters. Sometimes they will also give it in units of torr, T-O-R-R, and that is just a 1-to-1 conversion. For physics now, pressure a lot of the times is given in pascals. In pascals, so pascals is the same as newtons over meters squared. And let's think about this one a little bit more. We know the formula for pressure is force over area. If we want to figure out the units for that, we know force is the same as mass times acceleration, and area is the same as distance squared. By distance, I just mean like some sort of side length x, you know. Area is length times width. You're going to get a distance and square it. And so the units for that would be mass would be kilograms, and acceleration would be meters per second squared. Distance, we're going to use meters again, meters squared. Okay, this might seem way more confusing than just pascals, but if we remember all of this, it's the same as 1 Newton, which is the unit for force. So we can say that Newton over meter squared, and that is the same as pascals for pressure. That's how you get there. Lots of unit conversions. Something you need to know, pascals is just used for pressure. That's the SI unit for pressure. All right, moving on to energy and work. We have joules. Now, 1 joule is the same as 1 Newton meter. All right, and the way that we can think about this one is through the work equation. So we know from our physics equation sheet that work is equal to force times displacement. Again, like we said up here, force is mass times acceleration, and then we have that distance there. We said the units for mass is kilograms. We said the units for acceleration is meters per second squared, and we said that the units for distance is just meters. All right. And this here, we said that that is equal to 1 Newton because that is what force is. So we're left with Newton meters. So that is work. Work is in the units for work is Newton meters. I hope I'm not being more confusing, but if you are given a physics problem that you are not quite sure how to solve, it is very helpful to look at the units of the answer choices because the answer choices will always have units attached to them. And you'll get lucky if all of the answer choices have the same units. So let's say you're given a force and you're given a distance and it says to find the work. You can't remember what the work equation is, but you see that all of the answer choices have the same units of Newton meters. So that should immediately tip you off. Newton meters, okay, I'm just multiplying newtons, which is force, times distance, which is meters. So knowing these variables for the units can be very, very helpful, kind of decipher what you need to do, because the units will always have the same thing done to them as the numbers, if that makes sense. If you're multiplying the numbers, you're also multiplying the units. Moving on to power, we have watts. So 1 watt is the same as 1 joule per second. All right, and the easiest way to show this one is the equation for power. So we know that power is the same as work over time. Work, we said above, was force times displacement time T. So I'm going to use what we used up above, and I'm just going to skip the kilogram meters per second squared, and I'm going to go straight to newtons. So I'm going to do Newton meters, because that's what we said work was above, over time. Okay, and what did we say Newton meters was for work? We said Newton meters was joules. We can put joules up here in the numerator, and then the units for time is seconds. So that is how we get power, is joules per second. Again, knowing the units might make your life a little bit easier for the multiple choice MCAT questions. All right, we've already been talking about force, but just to have it in writing, you can say Newton is kilograms times meters per second squared. And we got that by saying force is mass times acceleration, which is the same as kilograms times meters per second squared. All right, the last thing that we're gonna do is density before we move on to constants. So density is used by this variable called rho, and it looks like a lowercase p. That's what it looks like. So density is mass over volume. That's just something that you're gonna need to know, and just know that this variable rho is density. All right, let's zoom out. That was a lot of information. We have all of this so far. We went over the different SI units, and actually, to be a little bit more clear, I am going to highlight all of the SI units in blue so we can remember. 1 meter, that's an SI unit. 1 kilogram, 1 liter, seconds is SI units, Kelvin. Pressure depends on the units of the constants, but it's usually either 1 atm or pascals for chemistry and physics. Energy, work, power, force, all of those are derived from SI units. As we saw, joules, we derived that from newtons and meters, which are SI units. So if it's derived from SI units, it is an SI unit. Lastly, before we close out this video, we're gonna talk about constants that you're going to need to memorize for the MCAT. Sometimes they'll be nice and give you some of these in the passage, but they don't have to, unfortunately. We talked about this one a little bit earlier, but let's start with R, which is the ideal gas law constant. Use this an example for PV equals nRT. R is 8.314 joules per mole Kelvin. And what I mean is this is the usual SI value that you will get for R. If you are using the ideal gas law and you want to use 8.314, you're going to need to make sure that everything else is in SI units, the temperatures in Kelvin, stuff like that. All right, Avogadro's number. This was in our general chemistry formula map, but we'll put it here too because it is a constant. It is 6.022 times 10 to the 23rd, and the units are particles per mole. And this is what you multiply the number of molecules by to get the number of moles. So this is a good constant to know to transfer between molecules and moles. All right, so that was chemistry. I'm going to change the color so it doesn't get too confusing. The charge of an electron is 1.6 times 10 to the negative 19 coulombs. And coulombs is just the SI unit for charge. All right. Keeping up with physics, the speed of light is 3 times 10 to the 8 meters per second. Meters per second, that is SI units, meters and seconds. I've had passages where they give this to you. I've had passages where they don't give it to you. This one is fairly easy to remember just because the numbers are nice and pretty. But for example, Planck's constant, which is H, is not so pretty to remember. It is 6.26 times 10 to the negative 34 joule seconds. I've never had a passage that you needed to memorize this one for. They've always given it to you, but since it is something that you're technically supposed to know, they could be really mean and not give it to you. Planck's constant is what you use in the equation E equals HF, so energy equals Planck's constant times the frequency. That is in our physics equation sheet. All right, this one is pretty straightforward. The Earth's gravity, which is the same as gravitational acceleration, is 9.8 meters per second. But for the MCAT, most of the time you will be able to estimate this to 10 meters per second. Most physics class you will take will not allow you to use this assumption, but for the MCAT, just 10 is good. Gravitational acceleration is what you would use for projectile motion in the vertical plane. So that is the value of A, acceleration, that you would use. All right, the speed of sound in the air. This one, again, is not as high yield. And the reason that I'm specifying in air is because sound waves do need a medium to travel through. So this speed will vary based on humidity, temperature, pressure, stuff like that, because it is medium dependent. But the standard speed of sound in air is 340 meters per second. The last physics one that I'm going to write down here is the range of visible light. Again, this one is not as high yield, but I think it is good to know. It's not too much to remember. So visible light is between 400 around, it's actually a more precise number, like 423 or something like that, but just 400 is fine. 400 nanometers to 700 nanometers. Sometimes you'll get questions that have to do with this. Just knowing this range and about the range of visible light might make some questions easier. All right, one last one that I do want to talk about that I think is important to know is the density of water is 1,000 kilograms per meter cube, which is the same as 1 gram per centimeter cubed. Okay. There are other constants that you might hear, and I can put them on this note sheets before I upload them, like the threshold for hearing, columns constant, stuff like that. But those are stuff that you would very, very rarely see, and if they would, I would bet they would give it to you. But again, they technically don't have to. So I'll write those down on here before I upload the notes. I will also go ahead and highlight all of the numbers down here at the bottom just to make it a little bit easier to read. But that is all I have for units, constants, and conversions. This is really just the basis and the foundation of sections that will have math and chemistry in it. So mostly section 1. I use in, let's say, the biology section as well. You never know, always using math. But having the foundation of being comfortable with these variables and being comfortable with these units is very, very helpful. I will upload these notes to the link tree. They will be under physics, and I will put it as units, constants, and conversions. But that is all I have for you today.